Thank you everyone for taking the time to attend this training session today. My name is Sajad, and today we're going to be talking about ATSPMs, or Automated Traffic Signal Performance Measures. So, okay, let's get this started. Just to give you a little bit of background on who I am. Again, I'm Sajad. I've been with Miovision for the past 4.5 years. I have a civil engineering background, and my graduate studies were all in related to traffic and transportation engineering. Super passionate about traffic data and turning that into impact. And this has been my focus for the past few years in using signal performance measures and helping cities and customers turn that data into impact. So today, again, the topic is on signal performance data, and if we had multiple days in order to sort of get through this, this is what the course breakdown would look like. But today, I want to make sure that we're covering as much as possible here to make sure that you have a good understanding of what the performance measures are, why it's important. What does performance assessment mean at different levels of intersection level, corridor level? How can one conduct a before-after study using the metrics? And hopefully, if we have time, we can actually go through the traffic link portal and do sort of some hands-on report generation in the traffic link portal. So you'll get a much more closer understanding of what we're talking about here. So at the end of this, if you want to call it the course, hopefully you'll be able to describe what SBMs are, understand and interpret what each chart shows, and hopefully be able to assess the performance of an intersection corridor based on your objectives, and being able to provide recommendations. So I think I want to step back a little bit and sort of talk about the why a little bit before we get into the how and the what. So philosophically, what is signal performance measure data? Why does it matter? What's the importance of the continuous nature of it? So I think it's important to talk about that a little bit. So starting from the basics, ATSPMs, you might have heard of it, you might have not, but it's an acronym for Automated Traffic Signal Performance Measures. Different types of acronyms for us. Some people just call them SBMs. I think it's an easy way to address them. And this was basically just to give you a bit of a history around it. A few years ago, these were methods that were developed by Purdue University in collaboration with a number of public agencies in the United States. And the whole aim of it, which is quite interesting, was that let's tap into the cabinet that's at the side of the intersection, the infrastructure that's already available in the field mostly, and let's capture as much information as possible from the field, from sources that might not have immediately been, or not immediately, the purpose isn't immediately for traffic data, but let's use them to be able to, let's come up with innovative ways to be able to use them for performance evaluation. And really going back to the why of why this data is important, and why this approach is an interesting approach towards it, because it's a measurement of performance, and mostly from the perspective of the road user. So conventionally in traffic engineering, we have a lot of demand measurement, less performance measurement. So conventionally, we sort of measure demand, do some modeling, and then we try to evaluate sort of the performance. But you can imagine, like, even a simple capacity analysis study where we talk about level of service, it's usually just based on one objective. It's just looking at vehicles, for example, vehicle level of service. And there's a lot of, even for that, there's lots of assumptions associated with it, right? So we have saturation flow rate. There's a significant number of variables that can affect that, and a lot of cases, like, that's just being assumed, right? So capacity is to a large extent just being assumed, and so the whole philosophy behind, if we want to call it like ATSPMs or SBM data, is is to let's measure performance directly if it's possible, as opposed to modeling it and then sort of using some kind of model to be able to assess that. For modeling purposes, the data could still be used. So definitely this does not remove the need for modeling. Modeling is needed if it's not just about the current situation. If we want to see, okay, what will happen if I add this bike lane, or what will happen if I add this right turn lane. Modeling could be more realistic using this data. So allowing models to be calibrated against the actual data in the field to be a much better representative of the traffic performance. So if we wanted to sort of describe two different methods, there's really there's very simply put, in terms of signal timing, there's two approaches. The conventional approach is more about, okay, I measure demand, so get some data from the intersection or from the roadway, measure the amount of volume demand from vehicles, pedestrians, anything else. I model traffic, I evaluate, and I improve and optimize, if that's the objective. But the new approach is more about measuring performance directly, evaluating that against your objectives, and then improving and optimizing, and then sort of coming back again and repeating the loop here, where you can go actually back to performance measurement. So now that you've measured performance, you evaluate and you improve your optimize based on your objective, now you can actually go back to the data and measure performance again and see whether you've actually reached that objective or not. So it really turns that conventional approach of where it's sort of an A to B, more of a circular approach where it starts from performance measurements, again ends there as well too, to be able to really evaluate and understand the changes, the impacts that the changes made had on the road network, the true impact that had. So in that regard, so if we want to look at the ATSPM approach or the continuous base approach, for signal timing specifically, I advocate for a term called healthy signalized intersections. Different people might have different opinions about this, but this is the way that I've seen a lot of public agencies look at their network performance, is the fact that a healthy performing signalized intersection in a corridor is one that helps the agency achieve their objective. And whatever that objective is, it could be different for different agencies in general, could be different from location to location. So a location, you might want more equality between the different modes of traffic, or another location where it's a major corridor and you want to maximize throughput and minimize delay for vehicles. It's another location where it's a downtown area, queue management might be more of an objective, or a combination of these objectives. But the main aim is to use the ATSPM data, use the SBMs in order to be able to understand the performance against those objectives set and be able to see whether you're reaching them or not. So moving away from sort of a given approach towards signal optimization and moving towards more of a objective-based traffic management. And even if the objective is, I've seen this with a number of agencies, the objective sometimes is to just reduce the number of citizen complaints about traffic. And even if that is an objective for the agency, that could be more data driven, right? If there's a complaint, like, why is that happening? Is it really a problem? What is the extent of the problem? And being able to understand like the true reasons behind it, I think is again, the continuous nature of this data and the resolution of the data it provides, it helps the move towards that as well. So this sort of speaks to the different levels when we talk about healthy signalized intersections. Again, intersections that help you achieve your objectives. Uh, Based on the types of problems that I've seen with by analyzing, I think more than 500, 600 intersections in the US and Canada, these are really the types of problems that I've seen. If we were going to categorize them, we could categorize them sort of into four categories. And the categories are maintenance, there's operations, there's optimization and safety, and they need to work hand in hand, and they sort of start from the maintenance piece. And these are the areas that the data could really help reveal problems that need to be fixed before you sort of go to the next level. So for example, if your infrastructure at an intersection isn't working properly, so one of these infrastructure is detection, for example. If detection isn't working properly, if your PED detector isn't working properly, if your vehicle detection isn't working properly, that's a maintenance problem. And regardless of how good your optimized plan is, it's really no use. You're not reaching. It's not allowing you to reach your objectives because you have basic problems at a maintenance level, and the data allows you to reveal those issues and be able to address them. The next level is more I call it the operations category, and it's more about the prerequisites to your optimized plan. And these are the types of problems that I've seen happen very commonly. So these are issues like there's a coordinated corridor, and a coordinated corridor requires all the intersections, all the coordinated intersections to operate on the same cycle length in the time of day plan. If that's not happening, regardless of how well you've optimized or how good your offsets are, that's not able to run properly because you don't have the prerequisites to that. And a number of these kind of problems, operational types of problems, are actually quite staggering, I would say. Um, and other types of problems, it could be very simple. So for example, left turn movements that are just wasting green time, minor movements that are wasting green time for no reason. So there's a lot of things in the controls that this could happen, but it's important to make sure that maintenance level, operations level, these are all working properly. And now we can talk about optimization. Again, this is where objectives are really, really important. You can optimize based on your objectives, and ultimately these are all towards the ultimate objective of making the operations of an intersection safer. But the interesting thing is that even a maintenance problem, in my opinion, could turn into a safety issue because of the inefficiency that it's creating and could impact people's behavior. So that's sort of the different levels that the data can provide information on. There's also the continuous nature of it. So do I really need the continuous? Does this data need to be continuous, or is one snapshot enough? So based on my experience, based on what I've seen, again, in the past 4 or 5 years, um, things happen. Like the infrastructure that's out there in the field, as time passes by, just stuff happen, really. Detectors fail, there's clock drift issues that sometimes happen, and there might be some optimization problems that happen. So for example, the pattern of how road users behave changes based as time passes by. There's a new restaurant, for example, at this corner, or there's changes that are happening in people's behavior. And as time passes by, so even if you have, so if we have on the bottom right here, if we call it a health rating, even if we have some major signal retiming based on objectives, everything set, and we're happy, if we don't track against those objectives and make sure that sort of this operation remains healthy with the small tweaks, with identifying the small problems, as time passes by, that health rating will start to fall. And what will happen is that you're not going to be able to really uh, see the impacts or the effects of that good signal timing that was put in place. So it's the continuous nature of it allows these small tweaks to happen, and maybe you wouldn't even need a major signal retiming in 3 to 5 years because you've constantly kept the performance of the intersection or corridor based on your objectives at a healthy rate. So keeping that healthy really allows the agency reduce the redundancy around, first of all, keeping it efficient as time is passing by because of all of these things happen, and reducing the need for subsequent timings. So this is, we talked about sort of the why and sort of the philosophy behind it, but let's get into the data a little bit more. What is this ATSPM data that we talk about? Where does this data come from, and how it's being generated? So I think if you get an understanding of sort of the data sources behind it, I think you get a better understanding of the metrics. So if I wanted to just jump into the metrics directly, I think it would be harder to understand. But let's just start off with all the basic piece of information that's helping towards that. So there's really three main data sources for ATSPMs, or automated traffic signal performance measures. There's the controller data, there's detector activations, there's MAC address data, for example, for travel time. There's a fourth data source that I haven't put in here. It depends on the technology that's out in the field. But for example, if you have a Miovision Smart Sense, it would also provide you with computer vision capability, and that opens up the whole new opportunity in order to be able to assess performance and create performance measures. So we'll talk about that in a little bit, but the main data sources we're talking about here are these three. So signal controller starts off with, okay, what is the controller actually doing in the field? That basic piece of information there is the amount of red, green, amber that's being allocated to different movements. What is the phase termination? So what is this, a gap out? Was this a max out? Was this a pedestrian call? What was happening during that time? And then it's possible to create some interesting insights out of that, which we'll go through. Is once you have the phasing information of all the different intersections, now you can line them up and create an actual time-space diagram that's happening in the field, and seeing how that's looking like. A second piece of information that's mainly available in the field is detection, right? So there's detection available in the field, and that could be as simple as a sloop detector that the data could come into the system, where stop bar detection and advanced detection. So at stop bar detection, if an intersection has stop bar detector capability, of course it's used for actuation, but the occupancy of the stop bar detector can be used to generate some metrics around the performance of the intersection. So for example, you could imagine that, we'll get into it a little bit with the details, but you could imagine during the green time, the more a stop bar detector is occupied, it's an indication of the level of saturation, or sort of the volume to capacity ratio, if you want to put it that way, for that movement. And then we'll get into it, but like they've taken this information, and by combining it with the signal timing, occupancy during green, occupancy during the first 5 seconds of red, it's possible to generate some interesting metrics as to the level of saturation of different movements, and being able to understand that from a cycle failure perspective. There's other information that could be available. So again, if an intersection has setback detectors or advanced detectors, if some people want to call them that. Again, the purpose might not be specifically for data purposes, but that information could be used to again bring it in and capture it and visualize it for different purposes. So one could be just based on the arrivals of vehicles on the advanced detector, being able to get volume information, so an estimated volume, or based on the arrival on the vehicle on this advanced detector and syncing it up with the signal timing at the intersection, be able to get information on arrivals on red or arrivals on green. How many vehicles arrived on red? How many vehicles arrived on green? And be able to generate like platoon ratio information, or the quality of, or being able to assess the quality of progression. If there's other detection available at the intersection, that data could come in as well too. So the pedestrian button usage, and the metrics that can be generated around that. So pedestrian delay, for example, how long does it take from the time that a pedestrian pushed the button until they actually got the green green walk signal. So all of this data, so it's quite interesting that this is a unique way of taking what's happening in the field and being able to generate metrics in order to evaluate the performance of an intersection or a corridor. The third piece of data is MAC address data. So the way that we provide that is through Wi-Fi MAC address sniffing. So as a device is passing through an intersection, capture the MAC address, you capture the MAC address, the hash MAC address at a second location as well. And then based on that time that it took to get from point A to B, you can get travel time information, and we convert that into different metrics. Could be speed, different visualizations like the congestion scan that we'll talk about in a little bit. So these are the main data sources. Again, if there's computer vision capabilities at the intersection, like a smart sense device, well, that provides more information, right? Safety metrics, turning movement count information, and just opens the sort of with the SBMs. One of the limitations is that you're bound to the metrics that have some sort of detection available at the intersection. So if there's more detection at the intersection available that's assessing the performance of vehicles, most of the metrics that are going to be available are going to be vehicle-focused metrics. But in order to get metrics around vulnerable road users or pedestrian cyclists, that's a different story. You need computer vision for that, and that's the direction that sort of we're taking in right now. Is to be able to create multimodal performance measures, not to just focus on vehicles. So in another sense, this is what the data would look like. You can imagine that once you tapped into the controller, this is the signal timing information that's coming from the controller. So remember, we talked about the phase data that's coming in. You could imagine like we have the phase, there's the green and red, there's the pedestrian information. You can see below on phase 10 and 14 here, the walk, the flashing don't walk. And then all the purple lines are the detector activations. So all these performance measures that we're talking about, most of these are a combination of these pieces of data put together in order to generate the performance measures. So let's go into so that was sort of the basics of the data. We're going to go into sort of metric by metric a little bit and just explain the different types of metrics that are available. Different systems might be, different ATSPM systems might be slightly different in terms of the data that they provide. But there are some metrics in here that are unique to us. But I'll try to go through as many as we can today, and hopefully we can go through some examples as well. So these are the types of performance measures that would typically be available at an intersection or in a corridor. We'll start to go through each one of these, but as you can see, like as we're going through, you'll be able to see where the data sources are coming from. So starting from the top left, congestion scan and travel time, these are coming from travel time information. So that Wi-Fi data that we talked about. Approach volume requires advanced detection in order to be able to get approach volume. It's also important to know what kind of detection gives you what kind of performance measure. So approach volume would require advanced detection. Some of the intersections don't have that. Arrivals on red, again, would require advanced detection because you need that information in order to be able to assess the number of arrivals on red and green. Green allocation is only the controller, so the percentage of red and green that's being allocated to different movements. I'll go into them in more detail, but I just wanted to tell you what kind of information needs to be available for each one of these. So occupancy ratio requires stop bar detector information. Pedestrian compliance, which is pedestrian signal compliance, requires computer vision capabilities to be able to see the pedestrian. Pedestrian delay requires a pedestrian push button. Phase interval requires just a controller because we just want to see how much red, green, and amber and what the controller is doing. Purdue coordination diagram requires advanced detection. Red light running requires computer vision capabilities. Simple delay requires stop bar detector information, and split failure and split trends require stop bar detector information. Turning movement count information, again, this is something that would require computer vision capabilities. So let's go through the sort of the metrics one by one and see what they are and what they're trying to show us. So the first performance measure we're going to talk about is the corridor congestion scan. This is I really like this graph because it's using travel time information. It's using travel time information along a corridor, and it is visualizing that in each section of the corridor. So section by section, it's showing you travel times along the corridor on a 24-hour basis. So the way that this works is that each section of the corridor, you can sort of see the sections here, which are grayed out. And we have the 24-hour duration on the x-axis or the horizontal axis here. The right side is showing one direction along the corridor, and the left side is showing the other direction. So if it's a north-south corridor, it will be north and south. It's an east-west, this will be east and west. And what it's showing us is a comparative, it uses sort of a comparative method in order to show, visually show travel times along the corridor. And the way that it's doing that, it's using travel time index. So what is the travel time index? It's basically the average travel time over the free flow travel time. And then that gives an index. So in the system, it's more interactive. So you can actually go on it and actually see what this number is, but this seems to be around maybe 3. So what this means is that during this time, which seems to be around 1 p.m., travel times are 3 times the free flow travel time. And free flow travel time is something that happens usually early in the morning. And that could be set and configured. So by dividing the average travel time over the free flow travel time, it allows us to get rid of distance between the intersections. So even if the distances between the intersections are different, the index allows us to be able to do a apples to apples comparison between the different sections of the corridor comparatively. So congestion scan, again, this is a metric that uses travel time information. And the way that this could be used to assess the performance of a corridor is usually by running a trend. So you run a trend of this data for like 4 weeks, for example, 2 weeks, 4 weeks, whatever duration that you want. And you can start to gauge an understanding of where the bottlenecks are happening. So it really gives a good understanding of where and when the bottlenecks are happening. So usually corridor performances are limited by the performance of 1 or 2 intersections. So really good to understand where that's happening, when that's happening, and being able to get an understanding of that on a trend basis, not just on a one day basis. So again, this would require travel time information in order to get this information. The second piece of data that again I like very much is the split trend data. The split trend data, maybe it's better to explain it this way. So the split trend data, again, if you remember, we talked about stop bar detector information and combining that with the signal phasing and timing information. So you could imagine on the left here, imagine there's a queue of vehicles and they're waiting for a green light. The light turns green and they're passing along and the queue isn't able to clear properly. So what this is showing us is that there's probably going to be a high occupancy on this stop bar detector during the green, which we'll call a green occupancy ratio, and high occupancy on the stop bar detector just at the start of the red. So we're going to call the ROR5. So you can imagine every cycle for each movement that has a stop bar detector, you can basically put one of these dots or circles on this graph. So each cycle for each movement, the performance will live somewhere within this area. So either you have very high green occupancy ratio and just at the start of the red, you're still going to have vehicles remaining that weren't able to clear the intersection, going to be way up here. Or maybe that movement didn't use its green time effectively, or there wasn't a lot of demand. We're going to be down below in the blue here. So you can imagine that each, and then what this is again coming from Purdue's research is that they divided this graph into different areas, which is I found to be quite a good distinction. So you could imagine that the cycles that fall within this red box here, they're classified as split failures. Or the cycles that fall into this blue area, they would be more of a spare capacity, or in the blue area. So one way that we visualize that information is down below here, where you can sort of see the circles on the screen. But the other way that we do that, we take all of these different cycles that experience different types of performance categories, and we visualize it on a 24-hour basis on a stacked bar chart format. So let's look at this, for example. It seems like during this time, let's look at 4 p.m. So at 4 p.m., again, in the system, it allows you to hover on top and will tell you the number of cycles in the tooltip. But here, this is just a static image. But it seems like 3-4 cycles apparently are experiencing split failures. There's one that's experiencing heavy traffic. A couple of them are experiencing sort of OK zone, and then there's one that's sort of in the spare capacity area. I think it's a really good way of just looking at the performance of a movement, like just by simply looking at it, just seeing what the performance is throughout the day. And something that one would look at is, from a vehicular perspective, is the red area, right? So the number of split failures or cycle failures that are happening, when it's happening, how often it is, and be able to run trends on the data. So let's not just look at one day, but what does it look like a 4-week trend? From another perspective, spare capacity, again, it could be either good or bad, right? So it's a matter of the objectives again. So for example, you have a time of day plan in the middle of the day, and the major movement is showing a lot of blue or spare capacity. Like that, what does that mean? That means that the cycle lengths that are being determined during that time are probably higher than what's needed. So maybe we could shorten those. Maybe we could prioritize pedestrians in that case, or maybe we could reduce the delay for pedestrians during that time. So it really depends on the objectives. Each of these categories could be either good or bad, again, depending on the objectives. Or if I'm looking at a left turn movement and I'm looking at a lot of blue, that's usually an indication that there's spare capacity on that movement. So why would a left turn movement not terminate properly? So again, a question that needs to be answered, and it goes back to the efficiency of the operations of the intersection. That a left turn movement needs to be called, serviced, extended, and terminated properly. Like, why isn't that happening? And being able to investigate that. And these problems are very, very common, I would say, in terms of like operational wise. But just looking at this, this movement, which this graph would be available for each individual movement, you could see that the number of split failures that are happening during the PM peak here are significant. By looking at the performance of the opposing movement, or the conflicting movement, you can assess whether there's opportunity to be able to shave a bit of time from here and add it to there, and be able to balance out the performance. Again, goes back to objective. Someone might be happy with this graph if they're looking at the opposing movement, so they want to maybe keep the corridor moving, or maybe they want to provide more equality between the different movements. So again, goes back to objectives. You need to set that and then assess, look at the data based on that. Another type of graph that's again a part of the ATSPM offering is arrival on red and green. So this would require, again, advanced detection, how many vehicles are arriving on green, how many vehicles are arriving on red, and be able to assess that in different intersections if there's advanced detection available. And then one way that we visualize that information is through this graph. Point-to-point travel time, again, we looked at the congestion scan that was showing us travel time more of a corridor view, but the same travel time can be looked at from just a point-to-point. So what is the travel time between these 2 points, and what time throughout the day are the spikes happening, or what is the trend looking like, or what is the you can see those grayed areas. What is the historical range of the data of the travel times? So not to look at it from just a corridor perspective, but again, travel time is a part of ATSPMs, which I guess everyone's mostly familiar with, to be able to assess travel time between 2 points. This is a filtered travel time, so it's already past the filtering where it's removed the anomalies. Approach volume requires advanced detection again. So based on advanced detection and being able to visualize the vehicular volume data on a 5-minute bin basis, and again, be able to look at the trends, look at the, I think this was one of the interesting ones during this whole COVID situation, where cities wanted to evaluate how traffic has changed, and whether people are sort of respecting that social distancing and the lockdowns or not, and what the economic situation is. So this was one of the popular graphs during these times. Arrivals on red and green, remember we showed that on a corridor basis. You can have access to that on an intersection by intersection basis. So again, the red portion of this graph shows the count or the percentage of arrivals on green, of arrivals on red, and the green part shows the percentage or the number of vehicles arriving on green. The way that I've usually used this is in combination with the theoretical time-space diagram. So you have a theoretical time-space diagram, and you think this is what's going to happen, and you think that maybe 60% of the arrivals need to be on green, but once you check this, it's actually much more different than what you would imagine that's going to happen, and that's where it sort of raises the questions of, okay, what's going on during this time. Arrivals on red and green also can be used to generate progression factors to assess the quality of progression. So based on the number of arrivals on red and green, which is usually a good progression is usually between 60 to 80%, but depends on the cycle length as well. But yeah, this is another way to be able to assess the quality of progression that's happening. Phase interval, again, a good one. This mostly shows what the controller is doing, so the amount of red, green, amber that it's allocating different movements. For the major movements, you can actually see the cycle length. So in this case, it's not actually, we're not able to see that, but the type of operations, there's lots of information sort of hidden inside this graph that can be assessed. So what is the operation? What are the time of day plans? Have they been implemented correctly in the field? So the basic application of the phase interval data is to just see that, okay, is something that's on the paper actually happening in the field or not? And I've seen a lot of cases where there's a lot of issues here because they haven't been implemented properly in the field, or things just happen, right? There's controllers, sometimes things happen to them. They and sometimes they're not operating as in the way that we might think they're operating. And sometimes the problems are quite subtle. So even if someone's had an intersection, it's very hard to understand that this is an actual problem because the impacts are very subtle. So you could imagine that if a controller isn't able to keep the cycle length consistent for some reason, for coordination purposes, it's extremely important for offsets to operate on a consistent cycle length. And let's say this cycle length was set at 100 seconds, but due to pedestrian calls or another type of conflict that might be inputted into the controller might not be able to keep that cycle length consistent. And it's just playing around with that offset, right? And what's going to happen is that the coordinate that's going to impact coordination quite a bit, but it's a very subtle problem. Just by standing in the field, it's very hard to figure out that this is the actual problem that's causing this. Another graph that's very specific to ATSPMs is the Purdue coordination diagram. This is a graph that visualizes the arrivals on red and green as we talked about. So so you could imagine that each of these black dots on this graph is actually one arrival of a vehicle during the respect phase. So if the black dot is appearing during the red, it means that a vehicle arrived on red on the advanced detector, so before it reached the intersection, and it's shifted for that. And if it's on the green, it means that the vehicles arrive along. So you can see here, for example, during midday operations, most of the platoon is actually arriving on green. So again, this is one of those graphs that need to be looked at with the time-space diagram together, in order to assess and see, okay, was this what was intended to be designed, or is the behavior or something different from what's actually happening in the field? It's good verification. Occupancy ratio is just another way of looking at occupancy of the stop bar detector that we talked about. That was generating the signal performance measures that we talked about, like the split trend. But if you're really interested in seeing what is the percentages of occupancy, that's this is a graph for that. I'm just going to move ahead a little faster just to get to the examples a little bit. But split failure, again, that graph, if you remember, we just take that information on the split failures and the green occupancy ratio, red occupancy ratio, and we visualize it using that stack bar chart. But you can also have this view as well, where if you want to actually see the dots and where they sit. Simple delay is another ATSPM. It's more about, it's not the actual delay, it's the simple delay. So the delay between the time that a vehicle arrived and the time that they got a green light. This could apply to anything, right? So if you, for example, have some kind of detection that's able to detect cyclists, you can tie it into this graph, and you can actually see what the delay of the cyclist is in getting the green light. So yeah, so this is the delay graph. Green allocation mostly shows the percentage of green time. What is the percentage of green time that's being allocated to different movements at an intersection in terms of their percentages? And yeah, I really haven't found a ton of application for this one, but it's just good to know. Pedestrian delay, this one is a good one. Pedestrian delay, in pedestrian delay, the height of the bars represent the amount of time that it took from the time that the pedestrian push button was hit to the time that the pedestrian actually got a green light. In this case, as you can see, it's quite variable, and it's because at this location there's an LRT train that's given priority. So sometimes if there's sort of two trains coming in the other direction, it takes quite a while for the pedestrian to get a green light. So it shows the number of activations as well too. So each one of these would be one activation, and the height of the bar would be the number of seconds that they waited in order to get a green light. There's report cards available as well. So all of these performance measures that we talked about, it's hard to just look at them one by one. But if there's a change that's made, easily by coming back to the report cards, it's possible to really quantify the impact. So there was a change that was made. How did it impact travel time? How did it impact, quantitatively, how it impacted each of these performance measures that we talked about? So it really brings the data together in order to be able to do before-after analysis. There's intersection report cards and corridor report cards. So this is more of an intersection-focused metrics, and the other one is more corridor level metrics like travel time or arrivals on red and green, for example, or any other metric that you feel needs to be on this page. Another metric is a time-space diagram. So again, if you line up the phasings together, this would provide you with a view of what the actual time-space diagram is that's happening in the field. Of course, the slope of these bands, the blue band and the purple bands that you can see, they're in two directions of the corridor. And the speed can be set, right? So if you're setting the speed to the vehicle speed, the slope of this line would set that, and you're able to see that the bands that are happening in both directions. It's a good verification just to make sure that this is what's happening in the field. Again, just making sure that things are implemented properly, and what you think is actually happening in the field. These are mostly turning movement count information that requires a smart sense or computer vision capabilities. So again, being able to see daily or 24/7, 365 days of the year volume data through computer vision capabilities. This was an interesting one where a typical weekday traffic is what it looks like on the top left. Typical weekday traffic with pedestrians at a very busy location, 46,000 pedestrians per day. And then this was in downtown Toronto. Raptors Parade, you can see that the number of pedestrians significantly increased, and there were times throughout the day that there were no vehicles, of course, because it was blocked to that. But yeah, good, especially in this, again, COVID situation, we've seen quite a bit of application of this volume data to be able to assess how things are performing. A red light running, and another performance measure that requires computer vision capability is red light running. So again, ATSPMs are not set in stone. Anyone could really expand beyond what's available out there. Again, very vehicle focused, but trying to expand beyond that. So red light running would be one of them, which is focusing more on the safety aspect. So the way to interpret this data is that there's black dots on the screen, and these black dots represent the vehicle being in the middle of the intersection according to that point in time within the cycle. So if the dot is within this yellow area, it means it was during the amber. If it's within this red area, it shows that it's how many seconds beyond red that actually occurred. So you can imagine the ones that are happening high up here are ones that are happening beyond 10 seconds. Our red light runnings are happening beyond 10 seconds. And this information, again, some aggregation features as well too, to be able to understand like the percentage and the total number of red light runnings per hour. Pedestrian compliance is another metric. Pedestrian compliance, similar to red light running, but just for pedestrians, like each dot represents one pedestrian being in the middle of the crosswalk in this point of time. If they are within this yellow area below, it means that they were in the middle of the intersection during the flashing don't walk. But if they are somewhere up over here, it means that they were in the middle of the crosswalk during the don't walk phase status. Really good. All these timestamps are available, and in my opinion, based on my experience, really good to get some of these timestamps going back to the video with the help of video, being able to assess why this is happening, what was the context, and it really gives a lot of context to be able to come up with the right countermeasures in order to address the non-compliance and the risk that the pedestrians are taking. Most of the cases that I've seen are cases where signal timings are heavily over-designed for the time that it's being set, for the time of the day, where pedestrians are just having a significant amount of delay for no reason. So it goes hand in hand with the ATSPM data in order to be able to assess what can be done about it, right? One thing is to know about it, but what can be done about it? Really, the ATSPM data comes into play to help assess that. I want to make sure that we're going through a few examples here. So I think I've got a few interesting examples to show you, just to showcase like how the data could be used. Again, like this is ATSPM is it's a pretty big concept, and it requires multiple sessions in order to really go through the details, but we'll go through a few examples here. So this is an intersection where the LRT train runs in both directions here at the intersection, and there's this left turn movement. There's a through here, T intersection, and I think the frequency of the train arrivals are, I think, between 6 to 10 minutes, so in either directions. And one of the interest that the city had during this time was, okay, like what is the impact that the trains or the preempts are happening on? The trains get a priority, and the city wanted to understand like how is it impacting traffic in general. So there's a graph to understand, first of all, what are the preempts, how often they're happening, what is the duration of the preempt. So being able to first understand, okay, how often this is happening seems to be quite frequent on both sides. And then the range of the preempts seems like between 50 to 100 seconds, and this just shows us that the frequency of the preempts. And then from another perspective, we're able to see how this is impacting coordination. So this was an intersection that was previously coordinated on the northbound through movement, for example. And as you can see above, you can actually see the cycle lengths, right? So the cycle lengths are nice and consistent. That's a coordinated intersection. And you can see the green and red being variable, and that's because of the actuation that's happening on the miners. So the miners, whatever time that they receive, if they have extra time and they gap out, it automatically dumps it on the major. So you can actually see that happening in different cycles. So what did the preempt do to it? So you can see sort of the after condition where it's barely coordinated anymore, right? So the preempts are impacting the coordination. It seems like the controller is constantly going through a transition mode in order to get back into coordination, and that barely happens because of the frequency of the preempts that are happening. So this is interesting because is there even a point to coordinate anymore here, right? Like, what is the point of coordination when it's not happening? Maybe it makes sense here to maybe prioritize some other modes of transportation. So maybe it's best to allow this intersection to operate in free mode, and maybe allow to minimize the pedestrian delays, for example, in this case, if they are high. So basically, coordinating during this time makes no sense. The traffic impacts for another problem that they were having at this intersection were some complaints coming from this left turn movement. So this left turn movement, there were complaints that, oh, we're taking too long. It seems like we're never getting a green light. So again, having a data-driven approach towards this really helps understand the problem and to be able to implement the right solution. So one of the metrics that we talked about, it was simple delay, right? So simple delay tells us, okay, how long is it taking from the time that the vehicle arrives at the stop bar to the time that they actually get a green light. So when the vehicle arrives, how many seconds is it taking on average? So what was happening, so that light blue one, that's the higher one, was happening in the before duration when they were receiving the complaints. Where in some cases, on average of I think 15-minute averages, vehicles here were waiting 150 seconds in order to get a green light. And the problem that was identified was that after the preempt was over, the way that the controller was configured was that it wouldn't go back to this movement if it wasn't serviced. It would go back to its own sequence, and until it would come back to this left turn again, there would be another train arrival, and it will skip this phase again. So it was skipping that phase multiple times. So this allowed the city to understand the problem, the severity of it, and then be able to implement a solution. So one of the solutions that they implemented here was to allow that left turn movement to be serviced twice within the same cycle before a preempt happens. So all these smaller cycles that you can see here, these are all the cases where that's actually happening, where that movement is being serviced twice within the same phase. So it allowed the user to do that, but let's quantify the impact. So now that the impact can be actually quantified, and we can actually see what the impact of that was. So remember the split trend graph that we talked about that showed us the number of split failures or cycle failures that were happening. We can go to the back of that graph, and we can see that in the before duration there were significantly more number of split failures compared to the after duration where the problem was fixed. So we actually quantify the impact that this solution had on the level of saturation at this intersection. So the number of red bars is considerably reduced here. And not only be able to visually see that, but using report cards to do before-after studies. So let's actually quantify the number of reductions in the number of split failures on all the movements at the intersection. So not just look at that one. So in this case, there was like a 25.8% reduction in the overall number of split failures that was happening at the intersection with this with sort of simple fix. I have other examples to go through. We sort of have 5 minutes. I want to make sure that that we're answering questions as well. Let's see if we have time. But does anyone have any questions until this point that they'd like to ask? Doesn't seem like we have questions here, but okay, there doesn't seem to be questions. I think we have time for another example. But if you have any questions, meanwhile, feel free to put in your question in the box. So moving along here, there's another example that I'd like to go through. It's around like pedestrian performance, pedestrian signal compliance. One of the metrics that we have is again pedestrian signal compliance. How many pedestrians are actually compliant towards the signal? How many are not compliant? And one of the areas of concern was like, how are these preempts having impact on pedestrian compliance, for example, which was an interesting one. So in this case, we were actually observing. So I'm going to show this video. So on this near side crosswalk on the left here, we're seeing a significant number of non-compliant pedestrians. And with the help of video, we're sort of able to go back and see, okay, what's going on? Why are there so many non-compliant pedestrians during this time? So did you see how the this is the eastbound movement up here that I'm showing with my cursor? You can see that the vehicle stopped here. And then the pedestrian starts to move, and then the gates come down for the other direction. But as you can see here, this just after a few seconds, it's green again. So the pedestrians actually thought that this is a green light for them, and they can pass, but it really wasn't, because this movement only turns red when there's a pedestrian called. It's not in conflict with any other movement. As you can see, the LRT is going, but yeah, the pedestrians are passing through. They got their light. But the interesting thing was that you see how that short red was happening? That short red was actually happening during different times throughout the day. So that was actually not supposed to happen. So that movement is actually not supposed to turn red when there's a preempt happening. It only should turn red if there's a pedestrian call. So with the combination with the ATSPM data, we were able to find how frequently that's happening. It was actually a problem. And there was these short 4 seconds that was happening. It was causing a safety issues. The pedestrian thought they could pass through, causing non-compliance. But it was interesting to be able to see that, how frequently this is happening, and the city was able to address this problem and reduce the number of sort of that risky behavior that was happening. So what I want to try to get at is sometimes these data sources sort of go hand in hand. It might seem like one would be interested in the specific data, but if you have sort of the entire suite of the data, you can start to investigate and see, okay, if this is happening, now I need to go and check the controller side and see what the controller is doing during that time and be able to understand that. So rarely, like there's one piece of information that one would use to come to a conclusion. It's usually a combination of them, and hopefully I've been able to show you here what the data looks like and what the SPM data is. There's lots to go through, but it's outside of the scope of today's presentation. So hopefully you've had the time to hopefully this has been useful to you and to just get a general understanding of ATSPMs.
Great, so we have one question here for you. So they're asking, are the pedestrian data and performance measures for crossing during the don't walk phases using data collected from video detection?
Yeah, so yes, so the pedestrian compliance is completely based on, first of all, requires computer vision capability in order to be able to see the pedestrian. And the way that we treat non-compliance, well, we're also seeing compliance is not just that. So in the graph, you can actually see the percentage of non-compliance, for example, which is taking into account the pedestrians who are compliant. But the whole idea is that, yeah, you would require computer vision, and the dot would be a case where the pedestrian is somewhere in the middle of the crosswalk in that signal status. So in this case, it was maybe 100 seconds after the red, after the don't walk status, and the pedestrian was somewhere in the middle of the crosswalk in this case. So yeah, hopefully that answers your question. There was a question about the phase data. The phase data is coming from the controller. It's not coming from computer vision. So this would require connectivity to the controller as well as computer vision. So yeah, that's a good question. Yeah. Okay, so thank you everyone for taking the time today. Feel free to contact us if you have any questions or you want some more information on this. But yeah, thanks for spending the time today.